This video is for Math 116, and this is on section 3.4, sum of a series. I'm going to start on page 116 just talk about the geometric series. So pages 114 and 115, it's some interesting stuff. If you're interested in these ideas, and I'll be happy to talk with you about them. But the problems themselves are all geometric series, and it's all about finding the sum of a geometric series. Okay, so let's talk about geometric series. We mentioned how they have a constant multiplier or constant ratio. So every geometric series is going to start out with a first term, and then every other term is just going to be based on multiplying that by the constant ratio, and so on. Okay? And so this is where we developed the general formula see, now I'm confusing sequences and series. Right? If this is a geometric series, then these are all going to be added to each other. There we go. All right. AR squared, AR cubed, and so on. Okay, there we go. All right, so if we want to write this in sigma notation, again, if you start with 1, the formula will be a little bit different than if you start with 0. Let's see, so I'll put the A times r to the k minus 1 if we start k at 1. And then, I'll put an n up there. And that's what I like to reserve the n for. And that n might be infinity, it might not, okay? So, let's see. Yeah, so if k is 1, this will be the 0 power, and you'll just get a. Then when k is 2, it'll be a times r, and so forth. Okay? Now you can also set this up with the k equal to 0 and ar to the k power, something like that. I think most of the textbooks that I draw from when I was writing this stuff start the k at 1 and make this k minus 1. Okay? All right. So, let's see here. All right. So let's work on finding the sum of a finite geometric series. AR, this last term will be AR to the n minus 1. Okay? So we start k at 1. This is k minus 1. The first term is a. And then we have this final term, a times r to the n minus 1. All right. So let's say that this sum is equal to some value that we'll call s. All right? All right. Now, to find a formula for this sum right here, because this thing is just a representation. It doesn't give you an answer. It doesn't give you a number for what s is going to be. So what I'm going to do is I'm going to multiply this on both sides by r. Okay? So, over on this side, we'll get r times s. Over here, we'll get a times r, ar squared, ar cubed, ar to the 4th, ar to the 5th, and then dot, dot, dot. I'll put the ar to the n minus 1 in there. But then the last term is going to be AR to the n. And so what I just did there was I took this thing and I multiplied on both sides by r. Okay? And so that's how we got the bottom one. All right. Now, we've got these two statements. One saying that this original sum is going to be equal to s. And now this new sum that we've got here is going to be equal to r times s. Now I'm going to subtract the bottom one from the top one. Okay? I was just making a video for Math 70 about systems of equations. All right, so if we we subtract, look what happens. These cancel, these cancel, these cancel, these cancel. That will get canceled out. These two cancel. We'll be left with this one, and we'll be left with that a. We'll have a minus a times r to the n equals s minus r times s, right? S minus this thing. Okay. Now, factor out the s. That'll give you 1 minus r. So now we've got a times 1 minus r to the n equals s times 1 minus r. Divide on both sides by 1 minus r. And our sum is a times 1 minus r to the n over 1 minus r. So there's our formula for a finite geometric series, okay? So this is going to be the sum for a finite geometric series. Now, let's look at a couple examples, and then we'll talk about what happens with an infinite geometric series. Okay, let's see here. So, problem 2 is we've got this sum, k equals 1 to 7, 16 times 1/3 to the k minus 1. Now the key here in doing these problems is that our series has to be in standard form, okay? So that when we draw out the values for a, r, and n, okay, they're correct when we plug them in there, all right? So here, a is 16, r is 1/3, n is equal to 7. So this is going to be 16 times 1 minus 1/3 to the 7th power over 1 minus 1/3. Okay, well, let's do a little bit of calculation here. 16 times 1 minus 1/3 to the 7th power. Okay. That's kind of interesting. And then that gets divided by 2/3. What do we get out of this? So this is going to be 23.989 approximately. Okay. I think that this is, I mean, if you look at some of these terms, let's see, we're going to start with 16, and then we're going to have 16/3, 16/9, 16 over 27, and so on. So that's why we're not getting a nice whole number answer, is because we're adding all these fractions together. And so that gets a little bit messy. Okay. That's fine. Let's see, I don't want to erase the formula here. Okay, so we'll go ahead and erase this. Okay, problem 4. We've got k from 1 to 10, 2 to the k minus 1. Okay, well, so this is sort of standard form, right? We've got k starting at 1. Our power starts at k minus 1. It looks like 2 is going to be our value for r, because that's what's getting raised to the power, right? That's what creates that common ratio. We know that our n is 10, but there's no identifiable a, really. Now, you can think of a as being 1, right? If you put like a times 1 in there, and that turns out to be right. The way you can double check, what's the first term? Plug in 1 for k, all right? And then you can calculate what the first term is. So in this case, it'll be 2 to the 0 power, which is 1. All right. So now we want our formula. 1 times 1 minus 2 to the 10th power over 1 minus 2. So let's see here. So 1 minus 2 to the 10th power divided by -1, 1023. Now there are buttons in here and pre-programmed ways that you can enter these series, with these appropriate values, and the calculator will go ahead and calculate the sum of the series for you. If all you're interested in is an answer, that's fine, okay? But what I teach in these courses is not answers, it's methods. It's methods of solution. I was just doing this video for Math 70 about systems of equations. And that's what this content is about. That's what the curriculum is about, is methods of solution. If all we cared about was answers, we could just plug everything into a computer and have it spit out answers for us. But the difference between answers and methods is that if you learn the methods, you have the power, okay? You can write your own computer programs. You can program your own graphing calculator, okay, that puts you in the driver's seat. You're not dependent on the technology. Now, don't get me wrong. I use technology as much as anybody else, but I know what it's doing, okay? And when it tells me something that looks fishy, I look into it, and I have the knowledge to do that. And so that's what we're focused on here. And I have no problem if you want to poke around in the graphing calculator and look at how that function works, that's fine, okay? But I'll tell you what, it's based on this, okay? Somebody at Texas Instruments took this formula and programmed it into that calculator. That's all that's going on. And the same thing is true for all of the functions of that calculator. In calculus class, when we talk about representing functions with an infinite series, that's how your calculator calculates sine, cosine, and tangent, as well as e to the x and ln x, okay, is with these infinite series that have been pre-programmed into the calculators. All right, let's see here. Now, while I was rambling away there, I just erased our formula, so I will put it back up on the board here. So what do we got here? A times 1 minus r to the n over 1 minus r. There we go. Okay, let's see. So that was problem 4. Problem 6 is very similar. Let's look at problem 8, because that's a little bit different. Problem 8, we've got this from k from 1 to 8, 3 to the k power. Okay, now notice that this is not in standard form. This is k minus 1, this is k. That does make a difference, all right? R is still going to be 3, because that's what's being raised to a power. That's what generates that common ratio. N is going to be 8. But the value of A, again, plug in k equals 1. That'll tell you what the first term is. In this case, A equals 3. And you could rewrite this, right, as 3 times 3 to the k minus 1, right? Because if you multiply these two together, that would give you 3 to the k power. So now there's your A, there's your R, and there's our N. Okay, so this will be 3 times 1 minus 3 to the 8th power over 1 minus 3. So let's see what we get here. 3, 1 minus 3 to the 8th. Okay, and then we'll divide that by negative 2, 9,840. Okay, and problem 10 is very similar. I'll just do that one right here. I believe that's from 1 to 6 of 3 to the, what power is it? K minus 4 this time. Okay, so again, our N is 6, our R is going to be 3, but what is that first term in this problem? Well, like I keep saying, the easy way is just plug in k equals 1. Okay, when k equals 1, that'll give us 3 to the minus 3 power, or 1 over 27. That's the value of A. Okay, and you can rewrite this as 3 to the minus 3 times 3 to the k minus 1. Same thing I did over here. and when you multiply these two together, add their exponents, that'll give you 3 to the k minus 4. There's our value of a. All right, so 1 over 27, 1 minus 3 to the 6th power over 1 minus 3. All right, let's see what we get here. 1 over 27 times 1 minus 3 to the 6th power. Okay. So that's going to be negative 26 point something, and then we want to divide that by negative 2. So it comes out to be 13.481 repeating. And that tells me that this will be a nice fraction, 364 over 27. Okay. All right, so those are the finite geometric series. Now, let's talk about what happens for an infinite geometric series. So, with an infinite geometric series, this n now is going to go to infinity. So, let's see here. K runs from 1 to infinity, AR to the k minus 1. Well, here's the thing. If r is greater than 1 or less than negative 1, okay, this thing's going to get bigger. Let's take something simple like 3 to the k minus 1. K runs from 1 to infinity. That's going to be 1, 3, 9, 27, 81, 243, and so on. It's just going to keep growing larger and larger and larger. These terms are getting larger and larger and larger. We're going to have an infinite number of them. There's going to be no finite sum for something like this. Okay? But what if our r in absolute value is less than 1? And that says that r is a positive or negative fraction, okay, that falls between negative 1 and positive 1. So something like that. We've seen some of these before. Let's say we've got a half to the k minus 1 as k runs from 1 to infinity. So that, we'll start with 1. And then a half, a fourth, an eighth, a 16th. Now these things are getting smaller and smaller and smaller, tinier and tinier. So there's a good chance that we may come out with a finite answer for something like this, or at least an approximation that is, very, very close to it. And that's sort of the defining feature of calculus, is this question of how close do you need your answer to be? What is your margin for error? I can make sure that you're within that. Okay? That's sort of the nature of this. And how big that error is just tells you how far out in this series you need to go. In fact, there's a whole area of mathematics that does nothing but look at that, the relationship between how large the error is versus how far out in the series you have to go. Okay, so let's look at this formula and see what happens when r is less than 1 and n is infinite. Okay, r is less than 1, n is going to grow infinitely large. What's going to happen? Well, look at what's happening to these. If you've got 1/2, right, to some giant power, this thing is going to get smaller and smaller and smaller and become indistinguishable from 0. Okay? The bigger this denominator gets, the smaller the value is. And again, how small you need it to get is determined by your margin for error. So, as this thing gets smaller and smaller and smaller and smaller and approaches 0, that's going to cancel out that part of the formula. And so, all we're going to be left with is a over 1 minus r. Okay, so that's the formula for the infinite series sum. So now, if we look at this one, our A is 1, our R is a half, 1 over a half is equal to 2. Okay, which says that this, all of this stuff equals 1, because we've got 1 here, that makes 2. So I've always found that to be kind of interesting, that this series right here, a half, a fourth, an eighth, a 16th, and so on, adds up to 1. And that, to me, is related in some way to this Zeno of Elea's paradox about he used to create these paradoxes that seemed like they were reasonable, but it gave you this crazy result. So one of his was that the hare can never overtake the tortoise, because first he has to make up half the distance that he's behind. And in that time, the tortoise will move forward a little bit. Now he's got to make up half of that distance, and the tortoise moves forward a little bit more. I like to do it with approaching the wall, saying, you'll never get to the wall, because first you have to go half the distance, right? And then you have to go halfway of what's left, and then half of what's left, and half of what's left. And that's what's happening here, but this is saying that you will reach the wall, and we all know that you will reach the wall, okay? And some of that is in this, because the sum of this series is equal to 1. Okay, so let's look at some of the problems on the sum of an infinite series on page 118 over on to page 119. So let's see here. Problem 12. We've got an infinite series, k from 1 to infinity. 12 times a half to the k minus 1. So this is nice standard form. Looks like A is going to be 12. R is going to be 1/2. And we don't have an n in this formula. And so all this is 12 over 1 minus a half. And so, excuse me, that's going to give us 24. And this series would look like 12, 6, 3, 3 halves, 3 fourths, 3 eighths, and so on. Okay. Let's see what else we've got here. Problem 14. Problem 14. K from 1 to infinity. 3/5 to the k minus 1. Okay. So, let's see here. Our first term, A, is going to be 1. And you can think of that if there's a 1 times this outside there, right? Because this is in standard form. Or plug the 1 in for k. 3/5 to the 0 power is 1. And our R is equal to 3/5. And so our sum should be 1 over 1 minus 3/5. 1 over 2/5. So 5 halves, or 2.5. All right, problem 16. What do we have here? So, sum 1 to infinity, 1/4 to the k plus 1. Well, now this is not standard form because our exponent is starting with k plus 1 there. So let's plug in k equals 1 and find out what the first term is. All right, that's going to be 1/4 squared, or 1/16. Our r here is a fourth. So this will be 1/16 over 1 minus a fourth. So 1/16 times 4/3. Our sum is going to be 1/12. Okay, got a couple more problems. here's the thing. And there's a problem in absolute value that is a little bit like this, where if you recognize the problem right away, this is, what do they call this? This is called a divergent series. It doesn't have a sum. Okay, why not? Our r is bigger than 1. Our r is bigger than 1. This is going to equal infinity, or what they call divergent. Okay? Now the problem here is that if you don't recognize that, you can generate a value for a, generate a value for r, and claim that this has a sum of -2. It does not. Okay, it's never going to be equal to -2. For one thing, you're not going to have any negative numbers being added together. So how could it be equal to a negative number? And for another thing, this thing is going to get infinitely large. As you keep adding more and more to it, it's going to get infinitely large, and it's what they call divergent. So I just threw one of those in there to remind you that this formula for infinite series is only for r whose absolute value is less than 1. Okay? All right. Problem 20. So, k from 1 to infinity, -1/2 to the k plus 4. Okay, so our r is between 1 and -1. That's what we want. Okay? So r is -1/2. A, our first term, is going to be -1/2 to the 5th power, which is going to be -1/32. So our sum is going to be -1/32 on top, 1 minus -1/2 on the bottom. So that's going to be -1/32 over 3/2. And so our sum is going to be -1/48. Okay, so that's it for section 3.4, and I think that's it for chapter 3 as well. Okay, so for the rest of the term, our video is going to come out of chapter 4, which is about permutations and combinations. It's a little bit different than what we've been talking about so far, but again, I think it's kind of fun stuff. As always, if you have any questions on this, please let me know. Thanks.